Guys, welcome to another Try Hack Me video with Isma. And in this section, we will be talking about packets and frames. And the goal is to understand how data is divided into smaller pieces, transmitted across the network to another device. Alright, so let's move on to task 1. What are packets and frames? Packets and frames are a small piece of data that, when forming together, make a larger piece of information or message. However, they are two different things. In the OSI model, a frame is a layer 2, the data link layer, meaning there is no such information as an IP address. Think of this as putting an envelope within an envelope and sending it away. The first envelope will be packet that you mail, but once it's open, the envelope within still exists and contains data. This is a frame. This process is called encapsulation, which we discussed in room 3 in the OSI model. At this stage, it's safe to assume that we were talking about anything IP addresses. We're talking about packets. When the encapsulation information is stripped away, we're talking about the frame itself. Packets are efficient way of communicating data across the network devices, such as those explained in task 1. Because this data is exchanged in small pieces, there is less chance of bottlenecking occurring across a network than large messages being sent at once. For example, when loading an image from a website, this image is not sent to your computer as a whole, but rather small pieces where it is reconstructed on your computer. Take the image below as an illustration of this process. The cat's picture is divided into 3 parts when it is reconstructed, when it reaches the computer to form the final image. Sorry about that, y'all. Packets have different structures that are dependent upon the type of packet that is being sent, as well as come to discuss networking in full of standards and protocols that act as a set of rules for how the packet is handled on a device. With the internet predicted to have approximately 50 billion devices connected by the end of 2020, things quickly get out of hand if there is no standardization. Let's continue with our example of Internet Protocol. A packet using this protocol will have a set of headers that contain additional pieces of information to the data that is being sent across a network. Some notable headers include header time to live. This field sets an expiry timer for the packet to not clog up your network if it never manages to reach a host or escape. Checksum. This field provides integrity checking for protocols such as TCP/IP. If any data is changed, this value will be different from what was expected in the form, therefore corrupt. Sorry about that. Source address. The IP address of this device that the packet is being sent from, so that data knows where to return to. Destination address. The device IP address the packet is being sent to, so that data knows where to travel next. Moving on to answer the questions below. What is the name of a piece of data when it does have IP addressing information? That's a packet. Second question, what is the name for a piece of data when it does not have an addressing information? That's the frame. And that concludes this part. Moving on to task 2, TCP/IP, the three-way handshake. TCP, or Transmission Control Protocol for short, is another one of these rules used in networking. This protocol is very similar to the OSI model that we have previously discussed in room 3 of this module so far. The TCP/IP protocol consists of four layers, and is arguably just a summarized version of the OSI model. These layers are application, transport, internet, network interface, very similar to how the OSI model works. Information is added to each layer of the TCP model as the piece of data or packet traverses it. As you may recall, this process is known as encapsulation, where the reverse of this process is decapsulation. One defining feature of TCP is that it is connection based, which means that TCP must establish connections between both client and a device acting as a server before data is sent. Because of this, TCP guarantees that any data sent will be received on the other end. This process is named the three-way handshake, which is something we'll come on to discuss shortly. A table comparing the advantages and disadvantages of TCP is located below. Advantages of TCP: guarantees the integrity of data, capable of synchronizing two devices to prevent each other from being flooded with data in the wrong order, performs a lot more processes for reliability. Disadvantages of TCP: requires a reliable connection between the two devices. If one small chunk of data is not received, then the entire chunk of data cannot be used and must be resent. A slow connection can bottleneck another device, as the connection will be reserved on the other device the whole time. TCP is significantly slower than UDP because more work computing has to be done by the device using this protocol. TCP packets contain various sections of information known as headers that are added from encapsulation. Let's explain some of the crucial headers in the table below. Source port. This value is the port opened by the sender to send TCP packet from. This value is chosen randomly out of the port from 065335 that aren't already in use at the time. Destination port. This value is the port number that an application or service is running on the remote host. The one receiving data for for example, a web server running on port 80. Unlike the source port, this value is not chosen at a random. Source IP. This is the IP address of the device that is sending the packet. Destination IP. This is the IP address of the device that the packet is destined for. Sequence number. When a connection occurs, the first piece of data transmitted is given a random number. We'll explain this in more in depth further on. Acknowledgement number. After a piece of data has been given a sequence number, the number for the next piece of data will have the sequence number plus 1. We'll also explain this more in depth further on. Checksum. This value is what gives TCP integrity. A mathematical calculation is made where the output is remembered when the receiving device performs the mathematical calculation. The data must be corrupt if the output is different from what was sent. Data. This header is where the data byte of a file that is being transmitted and stored. Flag. This header determines how the packet should be handled by either device. During the handshake process, specific flags will determine specific behaviors, which is what we'll come on to explain below. Next, we'll come to discuss the three-way handshake, the term given for the process used to establish a connection between two devices. Three-way handshake communicates using a few special messages. The table below highlights the main ones. SYN. A SYN message is the initial packet sent by a client during the handshake. This packet is used to initiate a connection and synchronize the two devices together. We'll explain this further later on. SYN/ACK. This packet is sent by the receiving device server to acknowledge the synchronization attempt from the client. ACK. The acknowledgement packet can be used by either the client or server to acknowledge that a series of messages/packets have been successfully received. Data. Once a connection has been established, data such as bytes of a file is sent via the data message. FIN. This packet is used to cleanly, properly close the connection after it has been complete. RST. This packet abruptly ends all communication. This is the last resort and indicates there was some problem during the process. For example, if the service or application is not working correctly or the system has faults such as low resources. Diagram below shows a normal three-way handshake process between Alice and Bob. In real life, this would be between the two devices. So it's showing you what would happen in real life right here. A communication between Alice and Bob. Anyways, moving on. Any sent data is given a random number sequence and reconstructed using this number sequence, incrementing by 1. Both computers must agree on the same number sequence for data to be sent in the correct order. This order is agreed upon during 3 steps. SYN. Client. Here my initial sequence number, ISN, to synchronize with 0. Number 2. Server. Here my initial sequence number, ISN, to synchronize with 5000, and I acknowledge your initial number sequence 0. Number 3. Client. I acknowledge your initial sequence number, ISN, of 5000. Here's some data that is my ISN plus 1. And the table shows you an example of what it's talking about. How it's incrementing its numbers. Moving on to TCP closing a connection. Let's quickly explain the process behind TCP closing connection first. TCP will close a connection once the device has determined that the other device has successfully received all of the data. Because TCP reserves systems resources on a device, it is best practice to close TCP connections as soon as possible. To initiate the closure of a TCP connection, the device will send a FIN packet to other device. Of course, with TCP, the other device will also have to acknowledge this packet. Let's show this process using Alice and Bob as we have previously. The illustration, we can see Alice has sent Bob a FIN packet. Bob receives it. Bob receives this. He will let Alice know that he received it and that he also wants to close connection. I'm sorry about that. Using FIN. Alice has heard Bob loud and clear and will let Bob know that she acknowledges this. And here is an example. Moving on to answer the question below. What is the header in a TCP packet that ensures the integrity of data? That is checksum. Moving on to the second question. Provide the order of a normal three-way handshake with each step separated by a comma. And that is the question. You have your SYN, comma, SYN /ACK /ACK. And I do apologize if I'm not pronouncing any of this correctly. Moving on to task 3, practical handshake. Help Alice and Bob communicate by reassembling the TCP handshake in the correct order in the statistic lab attached to this task. Enter the value of the flag given at the end of the conversation into the question below. So we're going to go ahead and do this challenge. It's pretty easy. So first, this is the first one. Can you hear me, Bob? And then this would be the second one. Yes, I can hear you. Third would be this one. Okay, great. After that is data. After that is this one. After that is this. After that, this one. There you go. And this was a pretty easy one, number 3. So I'll see you in the next one. Moving on to task 4, UDP/IP. The User Datagram Protocol. UDP is another protocol that is used to communicate data between devices. Unlike its brother TCP, UDP is a stateless protocol that doesn't require a constant connection between the two devices for the data to be sent. For example, the three-way handshake does not occur, nor is there any synchronization between the two devices. Recall some of the comparisons made about these two protocols in Room 3. OSI model, namely UDP, is used in situations where applications can tolerate data being logged, such as video streaming or voice chat, or in scenarios where an unstable connection is not the end-all. A table comparing the advantages and disadvantages of UDP is located below. Advantages of UDP. UDP is much faster than TCP. UDP leaves the application user software to decide if there is any control over how quickly packets are sent. UDP does not reserve a continuous connection on the device as TCP does. Disadvantages of UDP. UDP doesn't care if the data is received or not. It is quite flexible to software developers in this sense. This means that the unstable connection result is a terrible experience for the user. As mentioned, no process takes place in setting up connection between two devices, meaning that there is no regard for whether or not data is received, and there are no safeguards such as those offered by TCP, such as a data integrity. UDP packets are much simpler than TCP packets, have fewer header. However, both protocols share some standard header, which are what is annotated in that table below. Time to live. This field sets an expiry time for the packet so it doesn't clog up your network if it never manages to reach a host or escape. Source address. The IP address of the device that packet is being sent from so that data knows where to return to. Destination address. The device IP address the packet is being sent to so that data knows where to travel next. Source port. This value is the port that is opened by the sender to send the UDP packet from. This value is randomly chosen out of the port from 0 to 65,535 that aren't already in use at that time. Destination port. The value port number that an application or service is running on the remote host, the one receiving the data. For example, a web server running on port 80, unlike the source port, this value is not chosen at random. Data. This header is where data bytes of a file that is being transmitted is stored. Next, we'll come to discuss how the process of connection via UDP differs from that of something such as TCP. We should recall that UDP is stateless. No acknowledgement is sent during connection. The diagram below shows a normal UDP connection between Alice and Bob. In real life, this would be between two devices. And it's showing you a conversation in between theoretically two devices, which is Alice and Bob. Moving on to answer the question. We have, what does the term UDP stand for? It stands for User Datagram Protocol. Next question, what type of connection is UDP? And that is stateless. Next question, what protocol would you use to transfer a file? And the correct answer is TCP. Moving on, what protocol would you use to have a video call? That's UDP. And that concludes this portion. Moving on to Task 5, Ports 101 Practical. Let me close this challenge real quick, but yeah, let's get started. Perhaps aptly titled by their name, ports are an essential point in which data can be exchanged. Think of a harbor and port. Ships wishing to dock at the harbor will have to go to a port compatible with the dimensions and facilities located on the ship. When the ship lines up, it will connect to a port at the harbor. Take for instance, the cruiser line cannot dock at a port made for a fishing vessel, and vice versa. These ports enforce what can park and where. If it isn't compatible, it cannot park here. Networking devices also use ports to enforce strict rules when communicating with one another. When a connection has been established, recalling from the OSI model room, any data sent or received by the device will be sent through these ports. In computing, ports are a numerical value between 0 and 65,535. Because ports can range from anywhere between 0 to 65,535, there quickly runs the risk of losing track of what application is using what port. A busy harbor is chaos. Thankfully, we associate application software and behaviors with standard set of rules. For example, by enforcing that any web browser data is sent over port 80, software developers can design a web browser such as Google Chrome or Firefox to interpret the data the same way as one another. This means that all web browsers now share one common rule. Data is sent over port 80. How browsers look, feel, and easy to use is up to the designer or the user's decisions. While the standard rules for web data is port 80, a few other protocols have been allocated a standard rule. Any port that is within 0 and 1024 is known as a common port. Let's explore some of these other protocols below. File Transfer Protocol. This protocol is used by a file sharing applications built on a client server model, meaning you can download files from central locations. Secure Shell, which is on port 22. This protocol is used to securely log in to systems via text-based interface for management. Protocol Hypertext Transfer Protocol on port 80. This protocol powers the World Wide Web, www. Your browser uses this to download a text, images, and videos of web pages. Hypertext Transfer Protocol Secure, or HTTPS, on port 443. This protocol does the exact same as above, however securely using encryption. server message block, or SMB, on port number 445. This protocol is similar to the file transfer protocol. However, as we all as files, SMB allows you to share devices like printers. Remote desktop protocol, on port number 3389. This protocol is a secure means of logging into a system using Visual Desktop Interface as opposed to the text-based limitations of the SSH protocol. We have only briefly covered the common protocols in cybersecurity. You can find a table of the 1024 common ports listed for more information. What is worth noting here is that these protocols only follow the standards. You can administer applications that interact with the protocols on a different port other than what is the standard running a web server on 8080 instead of 80 standard port. Note, however, applications will presume that the standard is being followed, so you will have to provide a colon along with the port. For practical challenge, moving on to practical challenge, open the site attached to this task and connect to IP address 8.8.8.8 on port 1234 and you'll receive a flag. So we're going to open this up. So we have IP address 8.8.8 at port 1234. I'm going to click connect and we have received the flag. Moving on to task 6. Continue your learning, extending your network. Join the final room of this network module, extending your network, and continue your learning and complete this module. Moving on to answer the question below. Terminate the static site lab deployed in 3 and 5. I'm going to click complete. And now we're going to join the extending your network room to continue your learning. I'm going to click complete. And we're done. Thank you guys.